Hello and welcome. Right now we're going to look at the support vector machine classifier or SVM classifier and try to understand how it actually works. Right, so suppose we have two linearly separable clusters, cluster 1 and cluster 2. Then we can logically think that we just need a line that separates these two classes to classify a new point based on which side of the line it lies on, right? So SVM does this with a few calculations. So basically it randomly chooses a line first. That may be like this, whichever way it is. After that's done, it optimizes the line based on the closest points to the hyperplane. What is the hyperplane? So these two are the support planes of this main line, which means that the objective of the SVM algorithm is to figure out a main line such that the distance between the main line and the support vectors or the hyperplanes is maximized. So the thing about these hyperplanes is that they touch the closest points of each cluster. So suppose that these two are the closest points from the main line, then these will dictate the distance from the main line to the hyperplanes. The angle of this line is based on the closest 2 points of each cluster. That's it. For linearly separable data points or data clusters, it's a very simple algorithm and it works very effectively for small training data sets or small data sets. Next up, we have linearly inseparable data. In this figure, we see two classes that are linearly inseparable. If I draw a random line like this, basically you just can't separate the data with a single line, right? So what can you do? What you do is you use something called the kernel trick. Suppose I want to separate this data using a mapping onto a higher dimension, which means that in 2D, this could be linearly inseparable, right? Let's take the example of Leaning Tower of Pisa to understand how it actually works, right? We have two sample circles here, okay? This one and this one. If you want, we can take another one as well, like this one. And I hope that's visible. Right. So this is our 2D data that we're seeing. If we draw a line to separate it, we just can't, right? It's not viable because the circular clusters that we have are not separable linearly. So drawing a line is pretty much pointless, right? So next what we do is we look at it a different way, in a 3-dimensional way or a higher dimensional way, right? So this kind of gives us a different view on it, this as well. So this point at the top here, or this section at the top, is basically this section over here, this one, and this section is this section. So basically we have two concentric circles, black and red, and we view it a different way as shown here. So now what we can do is we can get a different line that can separate these two clusters. 2D circular data, 2D concentric circles. If you view it from a 2-dimensional perspective, you can't draw a line that separates these two classes or clusters. But if you scale it to a higher dimension, then you can separate it with the orange line as shown here, right? So this is the same principle we'll use to separate this data with a line. Because in higher dimensions, when lines separate onto different levels, we can't use a single line, right? So using a plane will basically separate these two clusters of data that we have on two sides of that plane. And whichever side of the plane that the new data point falls on, then we can classify that new data point as that cluster. So I think that's pretty intuitive, because the entire point of the algorithm is to just form a decision boundary. Let's figure out how this dimension mapping actually happens, right? First off, we have 2D data. Suppose we can bump it up to a higher dimension, then we can section the clusters with the plane like we've talked. But what if the dimension is very high? Suppose we have data that has to be scaled to multiple dimensions, not just one dimension, right? So 5-dimension or 6-dimension or more than that. So if we want to scale it like that, if we map each 2-dimensional point to a 6-dimensional or 7-dimensional coordinate, it's going to take a lot of time and CPU power. So it'll be inefficient. So what we do is we start trying to learn the similarity measures. Okay. So basically we form a single decision boundary at the start. Okay. Any decision boundary. After that, we check the points closest to the decision boundary. Suppose we form a line like this or something, and then we check the points closest to the decision boundary, right? After that, when it's scaled to a higher dimension, we can use something called a kernel trick. Okay. The kernel trick helps us to find the similarity. So if we want to figure out the similarity of each point from the decision boundary, that will just be done using a kernel formula or a kernel trick. We don't have to necessarily map out each point to a higher dimension, because like we've said, a two-dimensional point has two factors supporting it, right? For this, it's just x and y. If we have 7 dimensions, that is 7 points that will support this single point in a higher dimension. So that takes a lot of time and resources, like we've talked about. What we do is we try to make the similarities help us. Rather than mapping it onto a higher dimension, we'll see in a higher dimension, how is this data point similar to this decision boundary right here that we've trained based on the training data. Now that we've established a proper measure of similarity, we do not need the necessary coordinates of each point on the higher dimension. That can be done using the kernel trick, and that saves us a lot of time and resources. So next, when we get a new point that we have to classify, suppose it's some non-linear data like this, what we'll do is we'll check the similarity of each point to the decision boundary, right, to the decision plane. So if the similarity is closer to the similarity of this point to the decision boundary, then we'll just assign it to the blue class. If the similarity is closer to, let's say, this point, then we'll just assign it to the red cluster. So that's basically how we use SVM, which is the support vector machine classifier. Now let's look at a code implementation of this algorithm. So first we import 3 libraries, NumPy, Matplotlib, and sklearn. And from sklearn we import the SVM classifier. We set up a checkpoint with the seed42. Then we initialize 2 classes, right? Class 0 and class 1. Where in class 0 we use random points, 20 random points that are in the second dimension, that cluster around 2, 2. Class 1 is going to be 20 random points that are again in the second dimension and clustered around the point 5, 5. So next we assign our x and y of the training data using our np.vstack. X basically just stacks these two sets of points vertically. So x looks like this. This is the x, y coordinate. So next, y is just going to be our class label, right? So 0 into 20 means the value 0 is going to be multiplied 20 times, and then we're going to append the value 1 that's multiplied 20 times, which means that we're going to have 20 zeros and 20 ones in a list, right? So we can just print that out to see what happens, right? So we have a full array or a list of values where the first 20 are 0 and the second 20 are 1, right? Now we're going to initialize a classifier from the SVM module, support vector classifier, with the kernel that's linear because our data is linearly separable, and our C value is basically the leniency value, which is a hard margin or a soft margin. So if our C value is going to be high, then the number of points between the hyperplanes and the main decision boundary are going to be less, which means it will take the closest point without considering anything else. But if we take a very low C value, then our decision boundary is going to have a lot of points between it and the hyperplanes. So you see the hyperplanes here, a lot of points are allowed to be inside, which means it's taking this point and this point as the support points, right? So if I put C is equal to 1, then we're going to be a bit more of a hard margin, which means that it's going to take a lesser number of points between the main line and the hyperplane, right? So next what we do is we fit the x, y values, which is basically the coordinates and the labels, onto the classifier. Now we take a scatter plot where our x coordinates are going to be the x coordinates, and again y coordinates are going to be the y coordinates, right? And C is equal to Y, just means that it's going to color it based on the class. So 0 is going to be a different color, 1 is going to be a different color. And C map, black, white, and red means that we're going to use like a color map of black, white, and red. S is equal to 60 dictates the size, and edge colors dictates what color the edges of each point are. Right. Next, we're going to plot the decision boundary and the hyperplanes. First, we have to get the axis limits, right? We need to get the limits of what our starting point is, ending point is, so that our decision boundary can pass through the entire plot and not just like start here, end here, start here, end here, or something random. So we get the limits using this bit of code. Then we form a grid where we initialize like 100 points, where the limits are the limits that we've derived. So 0 and whatever this limit is, 0 and whatever this limit is. This part of the code will reshape this grid that we've created using mesh grid into a 1D array. And .c will just group the x, y coordinates together, right? So next, what we do is we reshape it back into coordinates that we can plot out. So using the contour function from our plt.gca function, we can plot out xx, yy that we've calculated using the decision function, and plot it out with the shape and the colors and the levels. The levels are basically the hyperplanes and the decision boundary. So the levels will be -1, 0, and 1. And our line styles will be double hyphen for the hyperplanes and single hyphen 0 for the decision boundary. And that's basically how we try to visualize the SVM classifier and how it works. And again, we've looked at the C value as well. So 1 is a harder margin and a lower value might be a softer margin. So let's just check that out again. So if we have 0.05, a lot more points fall between the decision boundary and the hyperplanes. So yeah, that's basically the code implementation. So the important part of this algorithm is to figure out how the line or the decision boundary is selected for 2D data that's linearly separable, using hyperplanes that basically choose the closest points to the decision boundary based on our C value, hard margin or soft margin. Next, for non-linearly separable data, then we scale it up to a higher dimension, look at it a different way, and then we select a plane that separates these two clusters. This is done using a kernel trick where we calculate the similarity of the decision boundary and all the points, rather than just mapping out each point onto a higher dimension, because again, it's very resource intensive and it's inefficient when we take complex data. And yeah, that's about it for the SVM classifier. And yeah, keep learning. Curiosity is the only reason we've gotten this far. And I'll see you guys in the next one.